Boom. Hello and welcome back to Calculus 2, section 10.2, polar coordinates. So we're back talking about our prerequisites for Calc 3. Those of you going to Calc 3 will be using this a lot. Last time we talked about parametric equations, and now we're going to take care of polar coordinates. Now, polar coordinates are operating on the xy plane. We still have a point in space, but polar coordinates are going to reach that point in a different way than what you used with Cartesian xy coordinates. So what you are used to, and I'll label that as old, is to have a point 2, 5, like this, which was the point x comma y, and then you will locate that point on your xy coordinate plane by counting 2 in x direction and then 5 up. And the point would be labeled 2, 5, which is a point in space. So that was the way to obtain the location in the old, what we call Cartesian system, or rectangular coordinates. And you can actually see the rectangle it creates, which is the reason why it's called rectangular coordinates. Now, the new polar coordinates have r comma theta. R is the radius and theta is the angle. And the way they operate is you are assigned, let's say, 3 and pi over 4. You are going to first draw radius 3 on x-axis, and then you are going to take that point 3 on the x and swing that 45 degrees to snap onto the 45-degree line. So it's going to go like this, and it's going to end up there, and that point is 3 pi over 4. And believe it or not, lecture over. Right? So now you know how to come up with the points. Yes? It's not straight up. This is arch. Because you have the red. Yes, the red line is the string. Very good. Now, to graph other combinations, right? We have, I like to draw, let me draw this red as a guide to you. So, you have x-axis. This is your positive r. This is your negative r. These are your positive thetas. And these are your negative thetas. So this is a guide to graph technically anything. So negative thetas go clockwise. If you get a point with a negative theta, you go clockwise. Negative thetas are clockwise. Clocks are backwards. So tough luck. These concepts are older than clocks. How old are clocks? These clocks with arms and... Yeah, they're not that old.
Yeah, but the sundials work the same way.
Backwards. Do what? Backwards. Yeah. All right, so just as a as a practice, so I'll leave so you can see the diagram. I'm going to ask you to graph 2 points on 2 separate planes. So first point is going to be -3 and pi over 3. And the second point for the second plane, -3 and negative pi over 6, whatever. So draw those. Okay, so -3 will be on the left, so we draw the radius on the left, and we need to go positive angle pi over 3, which is 60 degrees, which is somewhere on this line, right? So when we there you go.
Also, the whole thing like that.
Yes, positive angles go this way, no matter where you start. -3 is over here.
Are they always going to start on the x-axis?
Yes.
Okay.
And now we go backwards in time for our point. Bueno? Everyone on board with me? So, your R is either on a positive x side or a negative x side, depending whether you have a positive or negative number. And then angles are either positive or negative, which means clockwise or counterclockwise, from wherever you're starting with your R. Now, if you use your eyes, you will spot that this coordinate, well, this graph still has x and y as axes. That means this point that we just had has its xy equivalent, right? And our job is to figure out what that equivalent is. To derive the formulas for conversion between the polar and rectangular world, one way or another, it is enough to consider a single case this over here is x, this over here is y. I don't need these braces. This is x, this is y, this is r, and here's your theta. Now, some students like to just memorize the formulas and which one goes which way, and some students like to reason and remember it that way. I always hated memorizing. So the way that I present this is the way that I like it. But if you don't like it done that way, then memorize the final result. So what I'm going to show you is how to derive all four formulas and how to logically sort out which one is for which conversion. So what I'm going to do is I'm looking at this triangle here, which is showing the same point right there. I can reach that point by using polar coordinates. You see r and theta involved, or x and y, right? So the same point is explained through both worlds. Now, all I need to do is to write four formulas, trig plus Pythagorean theorem, and then sort them out which one goes which way. So the first formula I'm going to write is sine theta. So clearly, sine theta is y over r. From where I can write y is equal to r sine theta. The next formula is cosine theta, naturally, which is x over r, which is x equals r cosine theta. The next formula is tangent theta, which is x, it's opposite over, so it's y over x, from where I can write that theta is equal to tangent inverse of y over x. And finally, I can write Pythagorean theorem that r squared is equal to x squared plus y squared, from where I can write that r is equal to square root of x squared plus y squared. Now, if you carefully observe these formulas, if I group the sine and cosine together and the tangent and Pythagorean theorem together, I got my conversions. Now, which one is going from polar to Cartesian and which one goes from Cartesian to polar? Well, a little bit of common sense helps there. Observe that for the first set, I have r and I have theta and I can compute y. Again, I have r, I have theta, I can compute x. So clearly this is polar to Cartesian, because if these two are given, I am able to compute y. And the second set gives you x and a y. So these are your x and y coordinates. So you have that to calculate theta and then to calculate r. So it's very, in my opinion, it's very systematic. So that's why I never memorize the formula. I just memorize the triangle and then from the triangle write four formulas and I know which one is which. Because to calculate one value, you have to have the two values from the other world. So the first two formulas are going from polar into rectangular, and the second set is going from rectangular to polar for conversion. So now, if you have your -3, negative pi over 6 point, and you want to convert that to xy world, you will simply use formulas above. X coordinate is r cosine theta, r is -3, and then cosine of negative pi over 6. So that's -3, root 3 over 2, and we get -3 root 3, sorry, negative, yeah. No. No, I'm right.
R cosine theta. What else?
R cosine theta equals -3 cosine over 2. And then y is R sine theta, which is -3 sine of -pi over 6, which is -3 times -1/2, which is 3/2. So the polar coordinate -3 pi over 6 is converted into -3 root 3 over 2, comma 3/2. So we are able to convert the points from one world into another. If you are given, let's say, I don't know, 5 and 12, and you want to convert that into R theta, you will be using the other set. So R is equal to square root of 5 squared plus 12 squared, which is square root of 25 plus 144, which is square root of 169, which is 13. And theta is the inverse tangent of y divided by x, which is the inverse tangent of y divided by x is 12 divided by 5. Now, change your calculator to radians or degrees and make sure you use the units. So I don't care whether you use degrees or radians. Those of you who are engineers, you're probably going to use degrees, and those of you who are mathematicians are going to use radians. Personally, I don't care because they're the same, but you have to put the unit. You can't just write 0.7 and walk away. 0.7 what? Is it degrees or radians? Right? So, what do we have? What did you calculate since you have the calculator? 67.38 degrees. You put a little circle there. So now, your point 512 converted into 13, 67.38 degrees. If you want to graph this, you are going to locate 67.38 degrees, draw a line, and then go 13 and swing to snap to the line. It's very, very simple. So polar coordinates are operating also on the XY coordinate system, and they are just a different way to get to the same location. The rectangular counts on x-axis and then counts on the y-axis to get to the point where the polar world draws the radius and then swings the radius to the point where we need.
Is it called polar because it's simply
Yes. Mm-hmm. So now, they are exactly the same. Well, that's what we are going to discover. Whereas they are the same in terms of accuracy or anything. They're dead on, all of them. So we're going to take a look. Now, we are done with the basics in terms of the points, graphing the points, converting the points. The next step in the evolution is a function. The function in polar coordinates looks like r is equal f of theta. So theta is the independent input and r is the dependent output. With this, you can do some really cool stuff. How many of you have the graphing calculator with you, TID 384? Okay, so we have at least 4. Good. So here are some tips for graphing. Nope. So for graphing, first what I want you to do is to go to mode and then switch to radians and switch to POL. It's polar. So push the mode button on your calculator now and change it to radians and change it to POL. Is it a graphing calculator? It has to. It should say.
Okay.
Right.
Yeah.
All right. Now, what you are going to do is you are going to go into Window. And put you have X min and X max, right? So X min -6, X max +6, Y min -4, Y max +4, and do not touch anything else. Don't touch the thetas and increments and steps and S scales. Just leave everything as is and just change these guys. X min to -6, X max to +6, and then Y's to -4 and 4.
Why is it specifically those numbers?
Wow. Because of what I'm going to do next. Because I want it to look nice. Now, when you go to Y equals screen to plug in the function, do you see that you now have R1 and R2 and R3 instead of having F1, F2, F3? That's because you switched to polar. Now it's looking for the polar input. And when you push the variable X button, it will be printing thetas. It will not be printing X's. Now, what I want you to type in is 4 cosine of 4 and then push theta. 4 cosine 4 theta. And then press graph.
Okay. That?
So just a basic cosine function in polar coordinates, right? Graphs a flower. Isn't that cool? Instead of getting the, yeah, I did actually, and they found it fun. So.
Environmentally friendly.
Yes.
Flower doesn't die.
So, do what? There are a lot of cool stuff. So, guys, you can get a lot of other stuff with this. The graphs that you couldn't get in the XY world. Now, going back to this. So, you are able to graph any function. Guys, this skill is important because you don't have the sense yet of polar graphs. You have zero exposure to it. You are used to your cosine function to look like a wave. But in the polar world, cosine function is a flower. You just saw that. So you don't have the sense for these functions. And having the calculator ready to graph and give you the visual of what you're dealing with, especially for the next section, is imperative. So this skill has to be there. You have to be able to graph and have to be able to visualize. Can we graph these guys by hand? Yes. It's very long, it's very tedious and very painful, but you can graph it by hand by simply assigning values of theta, computing R's, and then having the points. Each point has to be radius, swing, radius, swing.
We don't have this on the exam.
That's exactly what's on the exam, to graph by hand. Exactly.
You can do it, but not scale.
Not the scale, exactly. So now that we understand that the polar functions work differently than the functions that we are used to in our xy world, if we can convert one function to another. So what I'm going to do is I'm going to make this a little bit simpler. If you go into your screens, the graphs that you did, and let's say you say y equals 4 sine 2 theta, you will get again a flower, but this time it will have 4 petals and it will fit nicely into your viewing window.
So flowers and sine.
Yeah, sines and cosines are reserved for flowers. Now, eventually you are going to try and go crazy with really large numbers in front of theta, which will give you some really crazy shapes. So these flowers and things are nice for, you know, for these thetas less than 10, let's say. I mean, the numbers in front of theta less than 10. But, see, she's already having fun with it. All right, so leave that exploration for home. What I want to do now is I want to convert this to a function in terms of x and a y. And we know how to do this. We have to be a little bit careful, though. We do not have 2 theta anywhere. So I will have to use the trigonometric identity to write this as 2 sine theta cosine theta, and then work on conversion. So what I'm converting is 8 sine theta. Ooh, why did I say y? This is all r. Wow. No one said anything. R equals 4 sine 2 theta. R equals 8 sine cosine. All right. So now what are the formulas that we know? We know that r is the square root of x squared plus y squared. And we also know that theta is the inverse tangent of y over x. Yeah. Time to plug these in and replace all r's and thetas with their equivalent x and y. So r becomes the square root of x squared plus y squared. On the other side we have 8 sine of tangent inverse y over x times cosine of tangent inverse of y over x. Well, luckily we reviewed these types of problems last class, right? On Monday. You know how to deal with sine of inverse tangent. Exactly, right, very good. So you have your triangle, and you have your y, and you have your x, and this is going to be square root of x squared plus y squared, which you know it's r, right? So now your square root of x squared plus y squared, when you copy, is equal to 8 sine, and you are reading the inverse sine off of the graph, which is opposite over hypotenuse, so that's going to be y over square root of x squared plus y squared. And then you have that times cosine of inverse cosine of x over square root of x squared plus y squared. So sine kills off sine, cosine kills off inverse cosine, and we have this. What is left? What's left is 8 xy over square root times square root is just x squared plus y squared. Now we can make this a little bit better if we take x squared plus y squared from the denominator and multiply it to the left, where you get x squared plus y squared to the 3/2, which is equal to 8xy. There is no way that I can make this y equal to everything else, because This is a flower, guys. It fails vertical line test miserably. So it's not going to be a function y equal f of x. There's no way. There's no way in hell.
Quick question. My brain's kind of fried right now, but how did you move from square root of x to the y squared?
This is exponent a half. And this is exponent 1. This is exponent half. This is exponent 1. 1 plus a half is 3 halves.
It's squared in the equation above, so why is it not?
Where is the square?
Well, it is.
This is the square root times the square root is no square root.
Oh,
Right?
right.
Square root of x times square root of x is just x. Cool. So there it is. You can't really make this better. I mean, you can take the cube root of both sides because 8 has a nice cube root. So you can get, I'll just put alt form over here, and I'll just say square root of x squared plus y squared is equal to 2 cube roots of xy. If that's going to make you happy, if you cube root both sides. But there is no way that you can make this y equals everything in respect to x. Now, we converted it. Recall the old equation. R equals 4 sine 2 theta. Which equation do you want to work with in terms of derivatives and integrals? The one on top or the one on the bottom? One on the bottom, right? So this brings us to your question. You asked if one is more accurate than the other. And my answer was they're both perfectly accurate. They don't approximate each other or anything like that. They're all perfect in its own sense. However, we can use them to describe the same concepts. But what's going to be beautiful in one world is going to be horrifying in the other. These guys don't compete. They complete each other. All right? So when you look at the equation given, very nicely given, in the, just take y equal x squared. To show y equal x squared in a polar world, it has to be disgusting. Because y equal x squared is beautiful in the R, right? So polar coordinates deal with the curvature much better than what the Cartesian world has. I mean, this cyclic kind of stuff with sines and cosines and so on. So let's think and consider real quick the y equal x squared equation, which is in rectangular. We all know it's a parabola. I mean, you don't have to think about this. You know everything about this, right? But now I come along and I say, I want this in polar coordinates on my desk by 9 p.m., right? So what do? You go and you convert this using formulas. You know that y is r sine theta, and you know that x is r cosine theta. Everything has to be squared now, right? So if you do this, you get r sine theta is equal to r squared cosine squared theta. You can kill off one of the r's. R cannot be 0, right? It will kill the whole thing, so you can divide by r. It's okay. And what you get now is that r, right, when you divide cosine, is sine theta over cosine squared theta, which you can write as 1 over cosine theta, sine theta over cosine theta. And finally, r is equal to secant theta tangent theta. There's your equivalent for x squared in polar. What are you going to work with? You're going to work with a Cartesian, or you're going to work with polar in this case? Obviously, you're going to work with Cartesian coordinates, rectangular coordinates in this case, because it's much simpler. So these are certain things that hopefully you're now catching on, that these two worlds, again, they do not compete against each other. One is not more precise than the other. They are exact. They're both exact. But your equations are going to be much better in one world than in other, depending on what types of equations you have. And to complete the story for the entire lecture, we are going to take a look at the most basic shapes, functions that we have for both of these. So, rectangular world has, as the easiest equation, a vertical line, let's say x equals 2. And another easy one, y equals 2. So these are my easiest equation for rectangular world. Now, polar world has the following. So in polar, we have the easiest, right? Guys, you see that rectangular world is x comma y, right? So I just set x equal to something and I get the vertical line. I say y equals something and I get horizontal line. What happens in a polar world, which is r comma theta, blue, as I say r equals something and just leave it as is? What do I get? But remember, here's the trick. Do you see, when I pin down x is equal to 2, note that y took on all of the values from negative infinity to positive infinity. Right? You see that? So whatever the coordinate is that we didn't pin down took all of the values. Same for y equals 2. X is going from negative infinity to positive infinity. Y is pinned to be 2. It's a circle. Because your thetas are going from negative infinity to positive infinity. Well, 0 to 2 pi is in there. So it's a circle that is stacked. And it's going like this forever and ever and ever and ever and ever in circle. And so it's hurricane, right? R equals, so this is your equation, R equals to 2. It just gives you the radius and you get the circle. You remember what was the r equals 2 equation for the circle in the Cartesian? Yeah, it was x squared plus y squared equals 4, right? Look at it in polar. Hello, circles. We love you. We're going to do a lot of cool stuff next class with this. And then what's the other one? Obviously, theta equal a number, an angle. So what do I get? What do I get if I say theta equals to pi over 4? I just get an infinite line. Because the radius is now allowed to be every possible number. If I draw a 45-degree line, this is simply said theta equals pi over 4. Now note that if I pin thetas, it's going to go through origin, and it's going to take the angle of whatever that angle is. So I can have pi over 6, pi, right, any angle, 1 degree, 17 degrees, whatever. Every theta I pick is going to be a linear line that goes through origin. Now try to shift that up to have a y-intercept. You can, and you will see the the horrors of polar coordinates, right? You try to shift this somewhere, all of a sudden secant pops out of nowhere, right? So why? Because the lines are designed and nice in the xy world. You know y equal mx plus b, like 3x plus 2? Yeah, that's beautiful in xy. If you try to go at 3x plus 2 in a polar, you're going to get secants and stuff popping out. It has to be ugly because it was beautiful in the other one, right? So now you have the notions of the basic ones, right? What are we going to do next class? So hopefully you have 5 days now to play with the calculator and see basic graphs. Cardioid is a heart-looking shape. Cardio, right? Cardio, heart. So you will see all kinds of cool shapes in this, especially when you open your textbook and see what some of these look like, some of these graphs. So here is the picture of a cardioid. Right, looks like a heart. So cardioid, and you have, there should be a spiral somewhere in here. There it is. R equals theta. You know your y equal x was a 45-degree line. Y equals x, 45-degree line. R equals theta, spiral. Because radius, when radius was 0, theta was 0, that's a 0, 0. And as soon as they start increasing both of them, whee, you get the spiral. All connected, everything connected, yep. This is a beautiful graph showing you the, again, correspondence between the two worlds of Cartesian sine graph and your polar graph, with showing you that the first bump of the blue creates the first petal of the flower, and then the green one connects this one, and so on, and shows which way it goes. But if you are observant on your calculator, because these calculators are sluggish, you will see which way draw, right? You will see which way draws the flower every time you graph it. So a lot of cool things. They have all of these kinds of things. Here, make a butterfly. You have the function e to the sine theta minus 2 cosine 4 theta. You graph this, you get the butterfly in your calculator. So all of these things are in your textbook. Your textbook, if you don't have the flesh and blood version, it's in MyMATLAB. So you will, guys, you will go and you will try the shapes. Now, where is the problems? Yeah, we are done. So here are all of the different shapes, the homework, right? All of the different shapes that you can try on the calculator to get working. Then using a graphing utility, problems 53 to 60, to practice. Again, you have zero exposure to this prior to. If you do not spend time and practice these on your calculator, you will be always 100% lost. Because these graphs are not natural for you. You never dealt with these graphs. Now, you know what's going to be funny? The half of your chapter in Calc 3 is going to be based on this. Because your cylindrical coordinates and your spherical coordinates, which are 3D coordinates, have polar coordinates as base. Cylindrical coordinates are r, theta, z. And the spherical coordinates are r, theta, phi. So all that we learn right now, you are going to upgrade in Calc 3 to the 3D coordinates. So you are going to have Cartesian x, y, z, and then two spin-offs off of the polar, as I said, r theta z and r theta phi. So you will be upgrading this stuff. The sooner you get comfortable with these graphs and things, the better. And also try middle school method to graph these puppies by hand. That means you pick a column for theta, and then you have a column for r, right? To compute r, and then you have r comma theta, plug those points. Sure, it's going to, spend 30 minutes to get a quarter of the graph, but it's a worth experience to get used to this completely new creature that you are seeing now. That's it, guys. I will see you all in 5 days for calculus for this stuff. We get to do derivatives and we get to do integration. Integration between two curves, figure out the area of one petal, figure out the area between circle and a flower and stuff like that. So there's going to be a lot of cool stuff on Monday.
All right, see you there.
Yeah.
X squared.